Have you ever thought about how amazing it is that we can process so much information at once? Like right now, you're hearing my voice, you might be seeing something else, there could be background noise, but somehow our brains just take it all in and make sense of it, all in real time. It's something we do without even thinking about it.
Yeah, it's pretty incredible when you stop and consider it. And from the perspective of someone who works in AI, it's really highlights the challenge we've been facing in trying to replicate that kind of seamless, multi-sensory understanding in machines. We've made huge strides with AI that can handle text really well, or images, or even audio. But getting them to truly integrate all those senses in a way that feels natural and responsive, well, that's been a whole other level of complexity.
And that's exactly what caught our attention when we started digging into the technical rapport for this new AI model called Qwen2.5-Omni. It seems like they might actually be cracking the code on this. So, for today's deep dive, we're going to really try to break down the innovations behind how Qwen2.5 Omni processes and generates information from all these different modalities. We're talking text, speech, images, video, the whole works. And it does it all simultaneously in a streaming manner. Really impressive stuff. And we want to make sure we focus on the really novel design choices that make this possible.
That's exactly right. The technical report from the Qwen team is really the heart of what we're diving into today, and it's packed with really interesting details, especially I think when it comes to their unique approach to this challenge. Right off the bat, what really jumps out at you is the sheer breadth of modalities that Qwen 2.5 Omni can handle. It can take in text, obviously, but also images, audio, video, and then it can generate both text and very natural sounding speech as output. But I think, like you said, the really key takeaway here is that it does all of this simultaneously and in a continuous streaming way, which is really essential if you want to create a system that can engage in truly real-time interactions.
Okay, so let's unpack this idea of unified end-to-end multimodal processing. It sounds like instead of having a bunch of different models for each type of sensory information, they've managed to create a single model that can handle everything. Is that basically the breakthrough here?
I think that's definitely a core part of their approach, yes. The goal is to have one unified model that can perceive and understand all these different types of data together. And when they say end-to-end, what they mean is that the model is trained to directly map from those various inputs to the desired outputs, whether that's text or speech, without needing a chain of separate hand-engineered processing steps in between. And this unified, streamlined approach is really important, both for efficiency and to ensure the model's understanding is coherent across all the different modalities.
Okay, so we've got this unified concept. Now let's talk about this whole streaming aspect. Why is that so crucial?
Well, think about how we have conversations. We don't wait until somebody's finished their entire thought before we start processing what they're saying, right? We're understanding them as they speak in real time. And for an AI to be able to do the same, especially with dynamic inputs like audio and video, it has to be able to operate in that same continuous streaming way. It can't just sit there and wait for a whole audio clip or video to finish before it starts to figure out what's going on and how to respond.
It's got to be able to listen and watch in real time, just like we do. So how does Q25 Omni actually manage to do that with these continuous streams of audio and video? The paper mentions something called blockwise processing. What's the idea behind that?
Oh, that's a really clever innovation. So when you have a long sequence of audio or video, instead of trying to process the whole thing all at once, which would be very computationally expensive, the encoders in Qwen 2.5 Omni break it down into smaller, more manageable chunks or blocks. So for example, the audio encoder works on blocks of about 2 seconds of audio at a time. And the vision encoder does something similar, processing the video in these smaller, digestible chunks.
So you're saying the encoder is sort of like our immediate sensory perception, dealing with things moment by moment. But how does it tie those individual perceptions together to understand a longer event that's happening over many of these blocks?
Right? That's where the thinker comes in. And we'll get into this in more detail later. But the thinker is basically the large language model, the LLM, at the heart of this whole system. And the way they describe it in the paper is that they're decoupling the handling of long sequences. So basically, the encoder is responsible for figuring out what's happening within each individual block. What are the sounds in that 2-second audio segment? Or what are the objects and actions in this short video clip? And then the thinker takes those block-level understandings and uses its knowledge of language of the world to assemble them into a coherent understanding of the overall event as it unfolds over time.
Okay, so it's like our eyes and ears are constantly taking in these little snapshots and snippets, and then our brain is weaving them together into a continuous experience. And I think that's a really important design choice for anyone who wants to be able to process information efficiently. You don't get bogged down trying to understand everything all at once.
Exactly. And because it's working with these manageable chunks of information, the model can start understanding and reacting much faster, which is crucial for that real-time feel we were talking about.
Now, there's another term that keeps popping up, time-aligned multimodal representation, or TMROC for short. It seems like this plays a key role in making sure all these different strings of information are synchronized correctly.
TMROC is a really innovative part of their design. It's specifically intended to keep the different modalities, especially audio and video, in sync. When you're watching someone speak in a video, their words have to line up with their lip movements and their gestures. If those things are out of sync, it's incredibly jarring and makes it hard to understand what's going on.
Yeah, for sure. So how does TM actually make sure everything stays aligned in time?
So the way they do it is they actually interleave the audio and video data into a single sequence. Like they take a series of video frames and then they insert these little snippets of the corresponding audio in between them, like every 40 milliseconds or so. And then TMROC goes in and encodes information about where each element in that sequence appears in space and time. So it knows where something is in the video frame, like its height and width, but it also knows exactly when it appears in time relative to the audio.
So it's not just about location on the screen, but about pinpointing the exact timing of everything. Does this basically create a sort of unified timeline for the AI to work with?
That's a great way to put it. And here's the really clever part. For the video frames, they actually adjust the temporal IDs, those when markers, dynamically, based on the actual timing of the video. So what you end up with is this perfect correspondence where one temporal ID in the video lines up exactly with that same 40 millisecond chunk of audio. They're basically establishing a common time reference for all these different sensory inputs.
That makes a lot of sense. I mean, if you think about it, being able to represent audio and video in this precisely time-aligned way would allow the model to learn a lot more about how those things relate to each other, right?
Exactly. It can learn that this particular lip movement always comes right before this sound, or that this gesture tends to happen in the same time as this word. And those kinds of fine-grained, time-locked relationships are really important for understanding complex, multimodal things like human communication.
Okay, so we've covered this unified processing and this ingenious way of keeping everything synchronized. Now, how does Qwen2.5-Omni actually generate responses? The paper talks about a thinker-talker architecture that allows it to produce both text and speech at the same time. Is that something new?
It's a really interesting and novel design choice, yes. The thinker-talker setup is specifically designed to let the model generate text and speech concurrently without those processes interfering with each other. In fact, they actually draw an analogy in the paper to how we as humans use different organs like our brains and our mouths to produce different but coordinated signals.
So in this thinker-talker setup, who's in charge of what?
So the thinker, as you might guess, is the large language model, the LLM. Its main job is to process the input, whether it's text, images, audio, video, and come up with a text-based response. It's kind of like the brain figure out what to say.
And then the talker is the one that actually turns those thoughts into speech.
Exactly. The talker is what they call a dual-track autoregressive model, and it takes the output from the thinker, the text, and uses it to generate audio tokens, which are basically the building blocks of speech. And what's important here is that both the thinker and the talker are trained together end to end. So the talker isn't just getting the final text output, it actually has access to some of the thinker's internal representations as well, which lets it generate speech that's more nuanced and context-aware.
So the talker isn't just reading the text aloud, it's actually using the thinker's understanding to figure out how to say it, like the intonation, the rhythm, all those subtle things that make speech sound natural.
Yeah, that's right. And to make this whole speech generation process more efficient, they also use something called a Qwen2 tokenizer. It's a kind of speech codec that compresses all that essential information about how to generate speech in a really compact way. And what's really cool is that they don't require this strict word-by-word or timestamp by timestamp alignment between the text and the speech. This makes both the training and the real-time generation process much simpler.
That makes a lot of sense. When we talk, we don't always pause perfectly between words, and our speaking rate can vary a lot. This approach seems like it would give the AI more flexibility to sound more human.
That's the idea. It focuses on conveying the important speech information without getting bogged down in trying to match the text structure exactly, which leads to a much more natural and robust speech output.
Now, we've been talking a lot about the streaming aspect and how important it is for real-time interaction. What kind of design choices did they make to ensure that this model can actually keep up and respond quickly?
You're right, low latency is absolutely crucial for any kind of real-time system. And they actually highlight several really innovative designs in the paper aimed specifically at maximizing streaming efficiency. For one thing, there's this whole chunked prefill idea that come from the blockwise attention mechanism we talked about earlier with the audio and visual encoders. Because those encoders are already working with smaller chunks of data, they can start processing and generating representations much faster without waiting for the whole input to come in. The vision encoder also uses things like flash attention and MLP merging to speed things up even further.
So they're essentially giving the model a head start on processing by breaking things down into smaller pieces.
Exactly. It's like prepping ingredients while the rest of the meal is still cooking. But I think one of the most interesting innovations for streaming is this thing they call a sliding window DI-T. DI-T stands for diffusion transformer, by the way.
That sounds very technical. Could you break that down a bit for us?
Sure. So the talker, the part that's generating speech, uses this sliding window DI-T to create what's called a MEL spectrum, which is basically a representation of the audio frequencies over time. And then that MEL spectrum gets turned into the actual audio waveform that we hear. The sliding window part is what makes this whole thing work in a streaming way. It means that when the deity is trying to generate the next bit of the MEL spectrum, it only needs to look at a limited context of the surrounding audio. In their implementation, it actually looks at 4 blocks, 2 from the immediate past, the current block, and 1 block looking ahead into the future.
So instead of having to process the entire audio history to figure out what comes next, it can just focus on this little window of context.
Exactly. And this drastically reduces the amount of time it takes to start generating speech. By limiting how much information it needs to process, they can get the speech output flowing much more quickly. And they also use these techniques called flow matching DIT and a modified Big VGAN for the MEL spectrum and waveform generation, which are also designed to work in a streaming fashion. So this whole setup is really a novel approach to real-time speech synthesis.
It sounds like they've really thought carefully about how to optimize each part of this model for efficiency without sacrificing the quality of the output.
It's definitely a very sophisticated system. And of course, to train a model this complex, they had to come up with a pretty sophisticated training process. The paper actually outlines a 3-stage pre-training procedure.
3 stages. Can you walk us through that?
So the first stage is all about getting the encoders, the parts that process images, audio, and video, to understand the basic relationships within their own modalities and how those relate to text. Actually keep the LLM, the thinker, frozen during this stage and just focus on training the vision and audio encoders on a massive data set of paired image text and audio text examples. This basically lays the groundwork for the model to understand what it's seeing and hearing and how those things connect to language.
So it's like they're teaching the AI's senses how to make sense of the world. What happens in the second stage?
In the second stage, they unfreeze all the parameters, including the LLM, and train the whole model on a 6 more diverse data set of multimodal data. This includes not only image text and audio text pairs, but also video text, video audio, and a lot of pure text data as well. And they're talking about huge amounts of data here. 800 billion image and video tokens, 300 billion audio tokens, and 100 billion video audio tokens on top of all the text. So this stage is really about learning how all these different modalities interact with each other and how they can reinforce each other's understanding. One interesting thing they did here is they decided to use natural language prompts instead of more structured hierarchical labels for their data. They believe this helps the model generalize better to new situations.
So they're trying to teach it to understand the world in a more holistic way rather than just as a bunch of separate information streams. And what's the focus of the third pre-training stage?
The third stage is all about handling really long sequences of data. They train the model on sequences of up to 32,768 tokens, which is a lot. And this is important because it lets the model learn how to track information and maintain a coherent understanding over long periods of time, whether it's in a video, an audio recording, or even a long piece of text.
Yeah, you can't really understand a movie or a conversation if you can only process things in short bursts. It has to be able to follow the thread over time.
Exactly. And it's also worth noting that before they even start these three pre-training stages, they initialize the model with parameters from some of their other successful models, like Qwen2.5, Qwen2.5-VL, and Whisper Large V3. So it's like they're giving it a head start in each individual modality.
So it's a very carefully structured approach to building up this multimodal intelligence. What happens after all that pre-training? Is there any fine-tuning involved?
There's definitely a lot of post-training and fine-tuning going on. For the thinker, the LLM part, they do some instruction fine-tuning using a dataset called ChatML. This basically helps the model get better at understanding and responding to instructions in a conversational way, including instructions that involve different modalities.
And what about the talker, the speech generation component? How do they fine-tune that?
They actually have a three-stage process for the talker. The first stage is what they call context continuation, where they train it to predict what comes next in a speech sequence, given the previous context. Then they use something called direct preference optimization, or DPO, to improve the stability of the generated speech. And finally, they do some multi-speaker instruction fine-tuning, which basically helps make the speech sound more natural and adaptable across different voices.
So they're not just teaching it what to say, but also how to say it in a way that sounds smooth and engaging, and maybe even with different vocal styles.
Right. And they also use some in-context learning, or ICL for the talker, to work on things like speech continuation and even trying to disentangle the speaker's identity from the content of what's being said. And then to further improve the quality, they actually use reinforcement learning, specifically targeting things like word error rate and punctuation pause errors to make sure the pronunciation is accurate and reduce unwanted noise in the speech. And lastly, they have a speaker fine-tuning process that lets them adapt the talker to mimic specific voices if they want.
Wow, they've really gone all out in making sure the speech output is not only functional, but also very natural and high quality.
Absolutely. And I think it's clear that all this effort has paid off when you look at how the model actually performs. They've done some very extensive evaluation across a wide range of benchmarks.
Let's talk about those results. What kind of performance breakthroughs are we seeing here? What should people be excited about?
So they've tested the model on a whole range of tasks, looking at both understanding and generation. When it comes to understanding, so taking in audio and producing text Qwen2.5-Omni is either state-of-the-art or very close to it on a lot of key tasks. We're talking things like automatic speech recognition, speech-to-text translation, audio reasoning tasks, and even voice chat interactions. And they've significantly closed the gap with models that just work with text instructions.
That's huge. It's like it can understand your spoken commands almost as well as if you type them out.
Yeah, exactly. And when it comes to understanding multiple modalities and generating text, Qwen2.5-Omni is state-of-the-art on established benchmarks like OmniBench. It's actually outperforming other models that are specifically designed for handling multiple senses, the so-called Omni models. This really shows that they've cracked the code on combining information from different sources effectively.
So it's not just good at individual modalities, it's actually better at understanding things when it can use all its senses together. What about the speech generation side? How well does it do there?
Well, for generating speech from different inputs, their evaluation shows that their streaming talker actually outperforms most of the other models out there, streaming or not, in terms of both robustness and naturalness. They're highly competitive in zero-shot text-to-speech, meaning they can synthesize speech in voices they haven't been trained on specifically. And after fine-tuning on a particular speaker's voice, the quality gets very close to human level.
And I think one of the most impressive results is that Q2.5 Omni can perform just as well on end-to-end speech instruction following tasks as it can when it's given those same instructions in text. This is on really challenging benchmarks like MMLU and GSMAK. That's a huge deal.
It really is. It basically means the model can seamlessly transition from understanding what you're saying to reasoning about it and coming up with an answer just as effectively as if you'd type it out.
So we've got all these really impressive performance results, but what does this all mean in terms of practical applications? How might we actually see the technology being used in the real world?
I think the potential applications are really exciting. Imagine having voice assistants that are not only much more natural and intuitive to talk to, but can also understand visual context. Like, you could point to something in your house and ask your smart speaker to adjust it. Video dialogue and question answering could become much more sophisticated and context aware. Real-time translation of multimodal content, Like translating a video that has both spoken language and text on the screen could be dramatically improved. And I think we could see some really amazing new accessibility tools for people with different needs.
This is the kind of technology that really has the potential to change how we interact with computers and the world around us. What about the future of this research? Where do they go from here?
Well, in the report, they outline several key areas they want to focus on. One is obviously to keep pushing the boundaries of model size and speed. They also want to expand the model's output capabilities to other modalities, like generating images, videos, even music. And interestingly, they also point out some areas where they feel research is lacking, like in video OCR, being able to reliably extract text from videos, and in more sophisticated forms of audio-video understanding that really take advantage of both modalities.
So even though they've made so much progress, there's still a lot of exciting work to be done. It feels like this is just the beginning for this kind of unified multimodal AI.
I think you're absolutely right. Q.5-Omni is a major step forward, especially with its focus on streaming capabilities and this novel thinker-talker architecture. And I think it really demonstrates the power of building AI systems that can interact with the world in a more human-like way, processing and generating information from multiple sources simultaneously.
So as you go about your day to day and you experience the world through your own senses, all working together seamlessly, take a moment to appreciate just how complex and amazing that is. And maybe think about how a model like Qwen2.5-Omni is bringing us closer to building AI systems that can do the same. It makes you wonder, what kinds of new possibilities will this unlock? And how might it change the way we live, work, and interact with technology in the future?